Hello, everyone, and thanks for having me here. I'm working at the computational biology branch of the NCBI. As you know, NCBI hosts some popular services like PubMed, PubMed Health, BLAST, of course, and PubChem. And computational biology branch is a research arm of NCBI. So we are addressing several different bioinformatics issues in the branch, especially for our group is text mining group. So we developed some core research, address core research problems, and then try to make a solution. And if it's successful, it moves to the production system. So I'm currently involved in a PubMed search project. So in this talk, I'll describe a few recent efforts to improve a PubMed search experience. So PubMed is a literature repository and also a search interface. So as a biomedical literature repository, there are more than 27 million bibliographic records. And every year, 1 million new records are just added. As a search engine, so far, over 3 million queries are performed a day. And also, not to mention that there is also traffic coming from other search engines like Google. This is our This is our PubMed search result for the query cancer therapy. In default, documents are ordered by the dates, that these documents when these documents are entered to PubMed, and brief information such as title, authors, and journals is displayed. It also shows other menus, filtering options, for example, filtering options that related to queries. And there are 7 options for document sorting, but 2 popular options are most recent and best match. Most recent is a Boolean search. So given a query, a Boolean search is done after spell checking and query expansion. Best match is our name for relevant search. So the current mechanism will rank documents obtained from the BM25 ranking function using a learn to rank method, and use over 150 signals for learning to rank features. NCBI recently released a new search interface called PubMed Labs. PubMed Labs is our testbed for new features for PubMed. So as you see here, the search wizard page in PubMed Labs is simple and mobile friendly. So when you click a document, you can see an abstract page like this, which has a clean look. So the design is quite different from the regular PubMed. Okay, let's moving on. So in a very abstract view, PubMed search has 2 parts. First, it indices documents. So certain terms and features can be used for ranking. Second, when a query is entered from user, it computes how much each document is relevant to the query. So this talk, I will touch 2 issues. First, how to match a query and document, and what to index from documents. So the first part of the talk is how to match queries and documents. Word embedding models represent the meaning of the words as a vector in a low dimensional space or high dimensional space, depending on view. Word embeddings are mostly trained in an unsupervised setting. So we know that this is a huge benefit because we don't need a manually annotated set. But what about word embeddings in PubMed? we know that word embedding shows PubMed promising results, but PubMed search doesn't use the semantic representation of word embeddings yet. So for instance, without prior knowledge, it's unclear that F1, flu, H1N1, and influenza are related, but using word embeddings, we know that they are closely related. So now the question is how we rank documents using word embeddings. So for this, we utilize the word movers distance proposed by Kushner et al. In their study, word movers distance was defined as a semantic similarity measure, and k-nearest neighbor was used to classify documents. In Kushner's and Huang's papers, word movers distance showed very strong performance. But the thing is that the time complexity is a bit expensive for PubMed search. So the complexity is n to the power of 3, which is quite expensive. So for this reason, we want to modify word movers distance for PubMed search.
So n is the number of documents, I suppose?
I'm sorry?
N is the number of documents?
N is, yeah, number of documents.
So it's probably also linear in the...
It's not number of documents, it's a number of words here. Number of words is matching document to document, and then this n is number of words appearing in these documents. Yeah. So in this original setup, word movers distance is defined as the minimum cumulative cost required to move all words from a document to the other. So to solve this problem, we should minimize the first expression here. So where the T is a flow matrix between two documents, and C is a dissimilarity function between words from two documents. Each column and row of the matrix T includes normalized term frequencies. I'm sorry, but it's a bit hot here for me, so do you have any, like a tissue or something? Word. Yeah, I need tissues because I'm sweating like a dog. Okay, thank you. Yeah. Here is water. I have water. But it's, yeah. Okay. I think just me. Okay. So we can use the same formulation for PubMed search. Like I said, the speed. N to the power of 3 is not practical for online search. Second is because Korean document languages are different. Here, one example. For general users, flu shot is a common term. But in biomedical literature, influenza vaccine is more popular. And since we are going to use word embeddings trained on documents, we cannot use these embeddings to map words from document to words from query because they are actually basically in a different semantic spaces. So we simplify the word movers distance. So the flow matrix here is the same, but we just change the minimum to maximum and define Cij as the cosine similarity function. However, one condition was removed from the original formulation. So the complexity just is reduced hugely compared to the original formulation. So, but the thing is that only using this normalized term frequency is risky because it will boost the weights of common words. So for this reason, we added IDF to the term frequency. The result is very straightforward. the reasoning method is basically for each keyword is to find the document word that is the closest in the meaning. So if the M is number of query words and N is the number of document words, the complex is now OMN.
So could you explain the difference between the original formulation and this formulation?
Yep. So since from original formulation, one is to map words from document to words from the other documents, and the other formulation is the other way around. But since query and documents uses different languages, and you're going to use this word embedding trend on documents, we cannot map. You cannot use one condition, right? We can use, if ideally you can use both. Is going to be better, but since we cannot use queries for training word embeddings, we have to drop one and just simplify this equation by just dropping. So one is gone.
But you still have the IJ, and they're coming from different spaces, and you compute the cosine similarity between them, right?
Yeah, but we only see one direction, not the other way. So
they're still independent spaces. Do you change separate embeddings for the queries and separate embedding for the document?
The thing is that we can train word embeddings using queries. The thing is that it's hard to get noise-free queries. Yeah, there is a problem. Yeah, there is.
I'm not sure actually what you use here for I. So I suppose, let's say I. Actually, both I and J are words from the document, right? Because it's a one.
Now, for original word formulation, because it was for a document classification, one document, the other document. We now want to match query and documents. So now one document is a query and the other is just document, the same, right? And we use this word embedding train the documents. So we can map one direction, but we cannot map the other directions because we don't have good information for query semantic space. So we drop just one condition.
And the one direction is from query to document.
Yeah. Not document to query. Yeah.
And for every document, is it the average of the embedding in that document?
No. Now you have to maximize the cosine similarity between query and document using this matrix, full matrix T. So the solution of this one is, I just simply summarize here actually. So if you compute that, the maximum value you can get every time is when we match the closest word from document and query. So for each query, if we find the closest word from document, that gives always the maximum value because it's natural because they are closely related in a semantic space. Then it's going to give a higher cosine similarity. If they are the same, it's always 1, right?
And then you max, so for every document it has a number of words.
So for each query, find the closest one from document, and for the next query, find the closest one, and match those, and get some of those.
If multiple documents have the same word, then you have the similar.
Yeah. Yes, I'll mention about that in the later slides. Yeah. So okay. So, but the thing is that what embeddings we can use. We know that if word embeddings are trained on general domain, the main problem is out of vocabulary issues. There are many terms that don't appear in biomedical literature. And also, different contexts lead different word embeddings. So using general domain for word embedding is just not our concern. So now we want to use word embeddings trained on biomedical text because those reasons. The advantage of using So the advantage of using real-world embeddings such as word2vec is that they produce quite good performance without fine-tuning. So people use real-world embedding models a lot. The thing is that although it produces reasonable result, that to have a better performance, we need still a benchmark set and text-dependent tuning for word embeddings. And there are many choices for word embedding models: word2vec, globe, fat text. There are many more. But we noticed that from all those papers, we noticed that their performance varies a lot depending on task they used. So for this reason, we selected word2vec with skip-ram for our experience because it's fast and then it performs reasonably well. So here's how we trained word2vec and tuned the parameters. Text is from PubMed abstracts, and for parameter tuning, we use 400 manual label synonym pairs from PubTern variants. This set is synonym pairs we obtained from the hypergeomet test and the morphosemantic test. And we adjusted the parameters to have high recall on these 400 pairs. High recall means low precision, but so if we use word embedding features only, then this is a problem. But we're gonna merge these word embedding features with other features later. So to have all possible combination in earlier stage is a good method.
Is the idea here that you have like a linear projection of the embeddings that you learn with word2vec?
So this is for how to get a DC in the word move systems. So for getting good constant similarities, you want to train a tuned word2vec model for this set, because in search part, we need to get similar words be located together. So the baseline would be to have a certain gold standard set of synonyms and tune the parameters based on this. That's why, yeah.
So when you say parameter tuning here, do you mean actually modifying the individual parameters of every word embedding?
Oh, no.
Or
Just the general parameters. Yeah, it's like negative samplings and window size, etc.
So
in word2vec.
What's the model in which these parameters are tuned?
This is for word2vec. Yeah, so we use 100 for vector size and 10 as a window size, and we checked the different word2vec parameters and then used these parameters for our experiments.
So we first train all the embeddings for all the words with a particular frequency using word2vec, and then we tune them using another data set.
Oh, I'm sorry. No. Just we use these parameters to train word embeddings.
So
and
you no longer need word2vec then?
Those are the hyperparameters for word2vec, and you chose those hyperparameters.
yeah.
To get good recall on those 400.
Yeah.
Got it.
Yeah.
Hyperparameter tuning.
Yeah. So let's compare the search based on word move distance and traditional search. So for the query, negative pressure wound therapy. Traditional search only finds the exact same word appearing in text. So there's a match for negative and wound, but not for pressure and therapy. If you use word movers distance, we find more relevant words such as therapies and the short name of negative wound therapy, MPWT. Here's another example. For the query BRCA1 ubiquitinating activity contribute cancer, there are exact matches for BRCA1 and cancer, but not for ubiquitinating activity and contribute. But if we use word movers distance, we find more relevant words, proteins, stability, and lead. So for a preliminary test, we applied a word movers distance to Genomics TREC data sets. So this TREC set has 160,000 documents and 26 and 36 queries for TREC 2006 and TREC 2007. So the Genomics TREC here was actually to search relevant passages from full text. So it doesn't have document level labels. So we labeled each PMID by checking whether the document has positive passages or negative passages. So we label them based on this information. So this table shows the search performance in average precision. We compare the performance with some baseline methods, TF-IDF, PM25, and also using the centroid of word vectors from queries and also documents. So for TREC 2006, word movers distance is 19% better than PM25. For TREC 2007, word movers distance is 6% better than PM25. So this word movers distance is effective to find relevant documents when only some of queries appear in documents. So like Wally just pointed out, if there are all words appear in documents, then this word movers distance cannot distinguish those documents with all queries in it. But good thing is that no training is required. There are no meta parameters, and we don't need any dictionaries for term variant and synonyms. The weaknesses are, again, like I said, it cannot distinguish documents when they all include query words. Also, m times n for time complexity may not be fast enough, because always it depends on the length of queries or length of document. It may be still problem. So we first want to address this issue. So to overcome this issue, we want to combine word movers distance feature with other features using learn to rank or deep learning approaches. This OMN problem is rather easy because no matter what, this distance is to measure score between a query A and A document. So this can be easily parallelized. So let's first see merging word movers distance with other features using learn to rank. In conventional ranking models, we have to use a manually designed ranking function such as PM25, and also we have to tune parameters in PM25 to have a better performance. And also in recent days, using just one ranking functions is not enough for follow users' needs. So learn to rank is a good alternative to learn how to combine diverse features from different signals. So we want to use lambda mart for our purpose because it's a pairized ranking. So it's a better suit for our purpose. Also, lambda mart is also used for the PubMed relevant search now. So it's natural for us to use this lambda mart because it's just one addition to the existing features. So this is an overview of our strategy. So given a query, word-to-word distance scores are computed over candidate documents, and they are entered in the learn-to-rank framework as a feature. And the learn-to-rank reorder candidate documents using the word-to-word distance feature, as well as other features. So to examine the learn-to-rank approach, we collected 27,000 PubMed user queries and user click-through data as the gold standard set. The relevance of query document pair was evaluated based on two main factors. One is number of clicks from the search reader page to the document abstract page. The other is a number of clicks from the abstract page to its full text link. We found that this full text click is a better signal than abstract clicks for relevance. So we assigned 0.33 for the parameter mu. So we use more information from full text clicks. And also, not all PubMed abstracts have full text, but still some of them might be important. So for that reason, we still give us a very small score when full text is not available, but people clicked. In this test, we compared three approaches. First, BM25. Second is learn-to-rank combining BM25 and semantic similarity score between queries and PubMed titles. Third one is use learn-to-rank and combine BM25 and semantic similarity score between queries and PubMed abstracts. The table shows the performance comparison among these three approaches. Since it's a learn-to-rank approach, we used normalized discounted cumulative gain for evaluation. And as you see from here, BM25 scored 0.15. If we add PubMed titles and abstract, the improvement is 23% and 7% for using titles and abstract respectively. So the performance increase is larger when we use PubMed titles than using PubMed abstracts.
So these experiments, you're saying it's semantic similarity, but is this
word-to-word resistance? Yeah, word-to-word resistance. Yep.
And why are you comparing to BM25 as opposed to learn-to-rank without those features?
This just simply tests how much we can get improvement over BM25 if we add this word-to-word resistance. So it shows that
a lot of that could just be coming from learn-to-rank, not necessarily the semantics.
Yeah, that's true. Yeah.
So I guess a follow-up question: how does this compare to what you already have, the search method you already have on PubMed?
It gives not significant because we use many different signals, but it gives improvement.
So the existing one also gives around 18.18 NDCG?
No. Not like that. Yeah. If you can get that much improvement, it's going to be, okay, this is the one we should use for everything, but it's not.
No, I mean the absolute number for the NDCG metric with the current method. Is it close to these numbers, or is it much higher or much lower?
Is much higher than this one. Yeah. But not far from these two numbers. Yeah.
Is that because you use more queries to train the learning to rank model?
Yeah, for those, we use more queries. Yeah, and I think that also contributes. Yeah, you're bigger, the better. But yeah. Also, there's a, I didn't add here, but for this, we need to use relevant search result for click-through data information for training, not date order. Date order is just reversed time order. And we know that people tend to click more for just high rank documents. And it doesn't give a good signal for finding good relevance. So we only used click-through data from relevant search. But the thing is that the default option in PubMed now is time order, not relevance order. So we don't have, after filtering out some rare queries and some, then we get much less queries left after this cleanup. Yeah. So for the query, it's kind of hard. So we first want to see why using titles gives more performance improvement than using abstracts. So there may be several reasons, but one reason we can just clearly think of what is the web search interface itself. So for the query ischemic heart disease, Google displays titles of the retrieved document and the snippets from abstracts. However, PubMed shows titles of the retrieved documents and citation information. Since we used the click-through data from this interface, that it naturally gives more emphasis on titles.
Well, but you're evaluating NDCG at 20, which is human relevance labels, not evaluating on relevance labels, not click-through data, right? Your NDCG 20 is
Based on click-through data information.
click-through data?
Yep. Yeah, this is quite noisy, but it's a good indicator still. Yeah. So PubMed Labs is quite different. So in addition to titles and citation information, it also shows snippets from abstract. So if it's given to users and we train those click-through data information, we expect that different results might come out from the experiments. The ranking performance is crucial, but also is the processing speed. So we added the order movers distance feature to the PubMed relevance search engine and measured the processing time. So with 100 competing threads, 900 queries were processed per second, and it took average 100 milliseconds per query on average in our search scenarios. In previous slides, I explained our experiments using learning to rank for word movers distance. Now, I will describe a similar approach, but using neural networks. From earlier word movers distance experiments, it's clear that finding the closest word in meaning gives a useful signal for document ranking. So we want to apply this information for the Severin and Moskitis convolutional neural network approach. So in their approach, the input is query document pairs, and the output is relevance, positive and negative. In the convolutional deep neural networks, each convolutional network maps a document or a query to a semantic vector, and these are used to compute a query document similarity score here, and combined together with this symmetry matrix is combined with document and query and document symmetry vectors, and this is followed by a classification network. So we want to modify this one and add the evidence that can come from word movers distance. So we want to replace this part with this one. So inspired by word over distance, we replace the query document representation with a difference vector. So for each vector in a document, we find the closest query word and compute the difference vector between them. So we have one difference vector. And we also add two constant values by adding the length and the cosine similarity score between two words vectors. And in their approach, we could also add some additional feature for this following classification network. So for those, we added four more. So proportion of query and document words in common, proportion of query words in documents, and proportion of query biograms in the documents. So for this simplified approach, we used more queries because we need to store more training set for neural network training. So for this experiment, we used around 33,000 PubMed queries. And also we also used user click-through data for the gold standard. And in previous experiments, we used different levels of relevance, but for this, we used the binary relevance. Like the learning to rank approach, we also used NDCG at 20 for performance comparison. And for the baseline performance, we used BM25 and word over distance, but only using titles because we know that titles are better than using abstracts. So as shown in this table, our approach improves the performance by 9% over the Severin and Moskitis method, and by 5% over the word over distance method.
So can I ask, what is the motivation for using the binary relevance? Because you previously said that it's better to use the relevance.
Because this is also another our test that how neural network can play a role for our PubMed search. So in their approach, they use just binary relevance. So we just followed their routine.
I misunderstood. Thanks.
Yeah. So as a result, we can conclude that word over distance provides a good evidence to connect queries and documents. So what are the next steps for how to match? These are all about word embeddings mostly. So first, word embeddings represent each word using one vector. And that is a problem for ambiguous words. Second is a more important problem. Similar words versus related words. We need similar words, but maybe not related words, because this is one example. If a user enters P53, the synonym TP53 is a good. So we can, if we can retrieve documents with the TP53, that's a plus. But in if we use word embeddings, MDM2, this another protein, is also close to P53. The thing is that these two are not synonyms. They are closely related, but not synonyms. So like MDM2 is a negative regulator of P53. So some people may try to find the documents with MDM2, but I quite doubt that. So distinguish between similar words and related words is a huge issue. The last one is that I mentioned before is flu shot versus influenza vaccine. So people use different languages in queries, and also authors use different languages in documents. So how to connect them is a very important question we have to answer. Okay, wrapping up the document ranking. Now I move on to the what to index problem. So it's words versus phrases. Let's see this first example. Zinc, finger, and protein have all different meanings individually. But when they are used together, it forms very specific meaning. So it's a very specific protein. So if we use single word embeddings and just take just average of those embeddings in semantic and map into a point in the semantic space, maybe that may not be the right point. So, and in PubMed, we not only just indexing just like terms from documents, we use over 32 million compound words for indexing. So we add more terms to each PubMed documents. But what if we can carefully choose phrases that help improve search performance? This problem is also the same as text segmentation. So for instance, what is the best way to interpret breast cancer treatment? Breast cancer treatment as just one unit, or breast and cancer treatment? Another interpretation is breast cancer and treatment. They are all, depending on view, they are all reasonable, but what about in terms of a PubMed search? And so text segmentation is to capture constituent structure unit in text, and we want to divide text into meaningful phrases based on terms appearing on PubMed. One way to find phrases is to use co-occurrences. For example, Mikolov in his paper identified phrases using counts of unigrams and biograms, which is also similar to finding co-locations. So in a co-location problem, most people use co-occurrences. So we also want to use co-occurrences to find candidates for PubMed. This is the outline of our of how do we identify meaningful phrases from PubMed. So we first extract all possible text chunks using certain characters as delimiters, and we apply a statistical approach and for phrase identification and an empirical approach for phrase filtering. As a result, we obtained about 660,000 PubMed phrases. So the approach we use for phrase identification is the hypergeometric test. So given two terms, p-value is computed to determine whether they appear together by chance or not in PubMed. So we use a very high confidence level, 99%, as the threshold. So for example, for early lung cancer treatment, we first match early and lung and check the p-value. And in PubMed, early and lung doesn't produces higher than 0.01 p-value. So we segment and move on to the next two words, so lung and cancer. And we apply the hypergeometric test. And lung cancer is quite significant pair in PubMed, so we merge them. Also, we do the same computation between lung cancer and treatment. So after segmenting these texts, we get lung cancer treatment as a good phrase. So we add this phrase to the set. The next step is to apply an empirical approach for phrase filtering. So we used our BM25 scoring framework to detect those text segments that benefit the search when they're used as phrases. So this is not just, this is process optimized towards retrieval performance and also guarantees that each selected phrase is a coherent unit and improves retrieval performance. The problem of using this kind of framework is that, okay, we can try this and compare. The thing is that we don't have a gold standard set for this approach. Because to compare with or without word and phrases, phrases for PubMed search ranking, then we need a very large set of manually annotated set. But this is not an option we can use. So let's say we use a phrase as a query. And the query here is a breast cancer treatment, the same sort of experiment example. So in this document, there are two different ones. One is the document with the query words in title, and the other is a document without query words in title. So if you just skim through it, just based on these titles, that we know that document A is more relevant to the query breast cancer treatments than the document B. So we want to use this information for semi-gold standard set. So let's say this is, we want to use, so having this in mind, we use document titles as a pseudo-relevance judgments. And the search is done using abstracts only, and the relevance is judged by titles. So it's a easy setup because in PubMed, we have titles, abstract always. So using this strategy, we compare Boolean search with a phrase-based search. So if the phrase-based search provides better performance than a Boolean search, we pick those phrases for our set. Here are some noun phrase examples from our phrase set. So as you can see, they look reasonable. Of course, there are grammatically incomplete phrases, of course, not shown here, but this doesn't matter because as long as the performance is improved in terms of BAME 25 score, then we just pick up, and because it may help improve the performance. Our phrase study is useful for my search already, but there are also other clear applications. First, segmenting text. In PubMed, breast cancer and treatment are better split for breast cancer treatment actually. For sickle cell pain management, sickle cell and pain management are the good split. From these last three sentences, GS fusion protein expression, SF9 insect cells, and mad cow disease are identified as meaningful phrases. Second, like the Mikolov's experiments, we can train embeddings using segmented text. So for example, for this ischemic heart disease, Google not only returns the documents with the query, but also returns the document with the pseudonyms, coronary heart disease. So from this definition, we know that ischemic heart disease, coronary artery disease, and coronary heart disease are all the same concept. So a similar strategy can be applied to PubMed using word embeddings trained on segmented text. So the closest phrases of ischemic heart disease are ischemic heart disease with AE, coronary artery disease, and coronary heart disease. Flu shots, flu vaccination, and influenza vaccinations are all the same concept. Since influenza vaccines, influenza vaccinations, and seasonal influenza vaccines are also close together, we can think of clustering phrases with a similar meaning. So we can group all these together and use that for PubMed search. So what's next steps for what to index? The problem is the same as how to match. What are similar words? What are similar phrases? What are related phrases? Plus, we are not interested in all phrases for example, flu shot is a very important word, but on the semantic space, doctor's visit or physician's recommendations are also closely related, but we are not interested in those extra phrases. So to summarize, for how to match query and document, we simplified word-to-voice distance for PubMed search, and we also tested learn to rank and neural networks for merging word-to-voice distance and other features. For what to index, we applied statistical and empirical solution to obtain a phrase set, and I just briefly discussed potential application for PubMed search. I worked with Ziyoung Liu, who is the PI of our group, Nicholas Fiorini, and Sunil Mohan for the document ranking project. For PubMed phrases, I also work with Ziyoung Liu, John Wilbur, and Dan Kama. I also thank other group members for their support. And also, more importantly, this research was supported by the intramural research program of the NIH and LM. Okay, thank you.